Yeah, you can start.
Wait for 1 more minute and then get started here. Let's get started. Yeah, so today we will actually introduce a new model of computation, randomized computation. So far in this course, we started off with defining the class. We wanted to understand the complexity of solving problems and with respect to various resources. So we started off with defining the class P. Then we went on to define, which captured several of the interesting problems that we work with. And it was a very realistic model of computation. Then we defined this notion of non-deterministic time computation, which on the face of it is an extremely unrealistic model of computation. There's no model of computation that's non-deterministic in any sense of the word. But yet, the reason we worked with it was because it captured some very interesting problems that we care about. Traveling salespersons, vertex cover, SAT, it captured these problems and it helped us to study the interesting phenomenon behind these classes and problems. So we defined this model of computation. Then we let our imagination run a little more wild. We went ahead to defining alternating Turing machines. And as part of this flight of fantasy, we defined PH, which had no ground in reality. It was just fun, but yet it sort of gave us, it was figment of our fantasy, but yet it sort of, even though it was a figment of fantasy, it did capture certain interesting classes. For instance, it captured constant round debates. And we also saw that not only it captured interesting classes, it also helped us talk about things which did not involve alternation or non-determinism at all. For example, it asked if SAT has, you saw these time-space trade-offs, whether SAT has linear time, does SAT have an algorithm which is both efficient in time and space? And we showed that that is ruled out. And the only way we know how to do it is by going via this weird model of computation, the alternating Turing machine. That's one thing which we saw. We also saw, does SAT have polysize circuits? This is a statement which does not involve any alternation or any such thing, but we sort of gave evidence to the fact that it does not have based on the class, the polynomial hierarchy. So this is what we've been talking. So we will do this a lot. We will take leaps of fantasy this way later on in the course. We will define classes which have models of computation which are not grounded in reality, but have captured very well certain classes or problems that we care about. And that's why we do it. But today, for a change, we'll actually work with a model of computation which is possibly most grounded in reality, possibly even more grounded in reality than P. We'll talk about RP, who has his feet firmly on the ground, unlike PH. So, and even before I define what randomized computation or the RP or BPP, the corresponding probabilistic classes is, what we will see, we'll motivate ourselves with a few examples. We'll see the surprising effectiveness of randomness. We will see that, we'll see a few algorithms for which we can come up with very efficient randomized algorithms which are much, much cleaner and nicer, and then go on to actually defining the formal model of computation, the probabilistic model of computation, and define the classes, the relevant classes, RP, co-RP, BPP, towards the end of the lecture. Okay. So we're going to be working with randomized computation. I won't make any formal definitions. We'll just look at some motivating examples. And the first example which we will do is primality. So we're interested in this class. So as let me define it as a language. Prime, it is, I'm going to give a number n. So n is in binary, and written in binary. I need not say that. me use the symbol. The number n is n is prime. N represents the binary encoding of an integer. So this is possibly one of the most classic. So the basic problem here is given. The problem which we care about now is given a number n in binary, determine if it is prime or composite. I'm assuming everybody knows what prime or composite means. You should have if you've seen one of the problem sets. Certainly. And of course, this is a very fundamental problem in math. And we would like to come up with an algorithm that does this. And till about 15 years ago, we did not have a deterministic algorithm that solves this problem. So a few years, about 15 years ago, in 2003, Agrawal, Kayal and Saxena, this was a part of their PhD work from IIT Kanpur, gave a deterministic primality algorithm for primality. Those of you who have possibly taken the algorithms course last semester, Kavita's algorithms course, would have seen the AKS algorithm for the deterministic AKS algorithm. What we'll be doing today is not the AKS algorithm. We'll actually come up with a simpler. We'll discuss a randomized algorithm.
Prahladh?
Yeah.
In fact, we didn't see AKS. We saw Miller-Rabin.
Oh, you didn't see AKS. I thought you had done. So randomized algorithm for primality. So there are two randomized algorithms. So one is very well known. There are several of them. The two very well known. One is Miller-Rabin, and the other is Solovay-Strassen. So I thought in the algorithms course you would have done both the AKS deterministic algorithm and the Miller-Rabin randomized algorithm. So what I will do in lecture today is actually I'll do the Solovay-Strassen randomized algorithm. So because some of you might have seen Miller-Rabin already, so I thought we'll do the Solovay-Strassen algorithm and show you how nicely randomness comes to our rescue. So I won't give all details. The algorithm I'll present it completely, but it will need certain number theoretic facts, and I won't prove all of them. Some of them I'll state without fact while proving them. But yet the simplicity, you should just look at the simplicity of the algorithm. It's a very clean algorithm that will come up, check whether a number is prime or not. We'll talk about Solovay-Strassen. So to start off with, suppose n is some number, n is some integer, positive integer. I'm going to just build some theory. We'll look at Zn. This is not standard math notation, but I'm going to use it. Zn is going to represent the set of integers 0, 1, 2, 3 up to n minus 1. This is usually sometimes represented as Z and Z, but I'll use Zn for this one. And Zn star is going to represent those integers among this which are co-prime to n. So Zn star is a subset of Zn, set of which are co-prime . And this is something you would have known. If n was prime, Zn is actually a field. In fact, in that case, you would have called it, you would have seen this. This is the field FP. That is these numbers 0, 1, 2, 3 up to p minus 1 actually form a field. You can add them, multiply them. That is, what do I mean by this? What do I mean by they form a field? So you take any two numbers, all operations. So let me say this. In this group, Zn, I'm going to think of it as a ring. And what do I mean by the ring? So ring should have both addition and multiplication. But all operations are going to be perform mod n. Modulo n. So each time you overshoot n, you sort of take the remainder and come back, and that's what you do over here. And so this makes Zn into a ring. But furthermore, if n were prime, it's not hard to check that actually this not only forms a ring, it actually forms a field. And every element, every non-zero element has a multiplicative inverse. Okay. So Zn is a field if n is prime. Now let's look at Z. So let's look at the special case. Let's focus on the case. We're going to build some special properties that n has if n is prime. So let's look at the special case when n is prime and look at Zn at that point. In particular, let's look at Zn star. Zn star in that case is just going to be 1, 2, 3 all the way up to n minus 1. Everything, because it's all the numbers co-prime to it. In fact, all the numbers less than n other than 0 will be co-prime to it in this case, Zn star. So we can sort of look at, take any a in Zn star. Let's look at the number x square minus. So 1 second. How do I want to write this? I want to write this as, okay, let's write this x square minus a. So I want to find out what are the square roots of a in. This is a thing which we'll come to in another example too. But let's look at that is how many x's are there in F. So basically what I want to ask, how many here is there an x in Zn star such that x square equals a. Everything, once again, whenever I say equal to, everything is happening modern. I'm going to be dropping off modern from now onwards. So how many, firstly, let's look at it. It's a field. How many, what I want to ask is there an x such that in Zn star such that x square equals a? And more than that, let's do the other question. What's the maximum number of x that can be such that x square is equal to a? I fix a, and I ask you what's the maximum number of x such that x square equals a?
2.
Why?
Because the degree of the polynomial is 2.
So x square minus a equals 0 is a quadratic polynomial, and because this is a field, it can have only at most 2 roots. At most the degree number of roots. This is an important fact for fields, and we'll see another surprising consequence of this later in this one. So it has, there are, if it exists, there are at most 2. At most. In fact, if it exists, is there at most 2 or are there exactly 2?
I guess exactly, because x and p minus x would be, I guess, satisfying it.
X and p minus x, are they different or are they the same?
They would be the same, right? It would be same, right?
Are x and p minus x the same? Can they be the same? For them to be the same, what should happen? X should be equal to p minus x mod mod P.
So P
Which is
minus
what?
X whole square is P square minus 2PX plus X square. And
No.
you are
X is equal
modding
to P
it-
minus X mod P. So what would that mean?
What?
So can X and minus X be the same number?
X has to be 0 then.
Oh,
I mean, if X is P minus X mod P, then
P by
if P
2.
becomes 0, then X is
Then X
So
should
X
be
is
P
equal
by
to
2.
P. X is equal to P minus X. Therefore, that means 2X is equal to 0 mod P. So two things can happen. Either P is 2, in which case 1 is equal to minus 1, or you do have. So if let's also assume n is prime and it's not n is not equal to 2 for now. Let's take off the one special even prime case. Then in fact there are exactly two square roots. Of course, if a is 0, there is one square root and 0 is a repeated root. Okay. So now let's look at this map, which takes, let's look at this map. Let's look at the square map from Zn to Zn, which maps X to X square.
How is it that the case when there are no roots got eliminated somehow?
Huh?
The number of roots is at most 2. How is the
At most
case?
2.
How is
Either there are no roots or there are 2 roots. That's all I have said.
Yeah, okay. There could be a case where there is no root, right? Yeah.
I haven't said there are. So let's look at this map X going to X square. So it's taking Zn and mapping it to this. And in fact, the image of this is exactly those A's for which you do have, for which there are. So by what we have said, the image of this, 2 of these are going. So except there is one element which is 0, for which 0 is going to 0. And then for everything else, there are two guys going to this. And these guys have, and then there are some guys which have no pre-images. So is the picture clear over here? So what I want to say over here is every guy goes to some element over here, but once some element goes here, there will be another element also that goes to it, because because that element has to have 2 pre-images. In particular, if this is square root a, this will be minus square root a. They will both get mapped to a. Of course, 0 gets mapped to 0. Everything, this is a function. Everything from here is going to get mapped over here, but there are some guys over here which possibly don't have any pre-images. Now, how many guys will not have pre-images? So we are working with a special case. N is prime.
I guess it will be odd.
N is prime. So say N is P. So how many? What is the image of square of this function square? Rather, I just want the size of the image of function square.
You can
just give me a second. There's somebody at the door. I'll just be back. Sorry.
order P by 2. P by 2 plus 1 or something of that sort.
So once again, so P is odd. P is odd because it's not, we removed 2. So
P 1 by 2.
So 0 is one element in the image. Then all the other, then there are P minus 1 guys, and I want to claim the image can be only of this size. The image, there are only P minus 1 by 2 elements over here, because the remaining p minus 1 by 2, p minus 1 elements over here are all getting mapped, and they're all, it's a 2-to-1 mapping. Therefore, the number of guys here is only p minus 1 by 2. There are p minus 1 by 2 which do not have a pre-image. So I want to claim this map. So the image of square is image of square is exactly 0 union some set, which we'll call the quadratic residues. These are the things which have square roots. Quadratic residues, and size of QR of n, and QR of n is exactly of size p minus 1 by 2. QR of p. So I'm going to define A in Zn star. We'll say A is a quadratic residue if A equals x square for some x in Zn, and otherwise A is a non-quadratic residue. Okay. And the number of quadratic residues, the number of non-zero quadratic residues is exactly p minus 1 by 2. The number of non-quadratic residues is p minus 1 by 2. And 0 is a quadratic residue. 0, it depends whether you're going to call 0 a quadratic residue or not. So right now, I'm not going to call 0 a quadratic residue. It's a square, but it's a special kind of square. Okay. So far, so good. Okay. I'm just going to use, I'm going to define a new symbol called the Legendre symbol, which is it's more a shorthand notation for denoting whatever I have written so far. So Legendre symbol that's the Legendre symbol. It's defined when A is in Zn. So A and N it's defined when N is prime. N is prime and A any integer. And it's defined to be 0 if A is congruent to 0 mod n. It's plus 1 if A is a quadratic residue. Rather, A, let me write it as A mod n is a quadratic residue. And minus 1 if A mod n is a quadratic residue and A not equal to 0, and is a non-quadratic residue. The Legendre symbol is just a shorthand for writing whether it's a quadratic residue or not a quadratic residue. But I want to say there's a nice observation. Let's call it a fact. That if n is prime and A is co-prime, A is co-prime, A is not a multiple of n. There's an easy way to I want to check if a number is a quadratic residue or not. How would you do this? By the way, I don't expect you to come up with it off the cuff. If you know it, let me know. Otherwise, have you seen this? You might have known. You might have seen
everything.
Huh?
Maybe just square everything and check if it is.
No, one way, of course, you for square everything and find out if it maps to A. But notice that is, if we're talking, I wanted the whole class, this class is to do efficient algorithms. We're going to run in time which takes time as many time. If you're going to run one for every integer n, that's too long for us because n is got to given in binary. I want to find, is there an efficient way of doing it? Certainly that's one way of doing it. Now you would have seen that a power n minus 1 is congruent to 1, rather any, let's not call it a, let's call it, so x power n minus 1 is congruent to 1 mod n. From Fermat's little theorem or whatever, you would have seen this. Now, if a was a perfect square, and a was a perfect square, I want to claim that a power n minus 1 by 2 itself will be congruent to 1 mod n. Why? Because a will get replaced by x square, and then you have x to the power n minus 1. So if a, so I just want to make, before we write this fact, if a is a quadratic residue, a power n minus 1 by 2 is congruent to some x square n minus 1 by 2, which is congruent to 1 mod n. Okay. And actually, you can see if a is a non-quadratic residue, this guy, a to the power n minus 1 by 2, will actually, notice a to the power n minus 1 by 2, what can it be? You know a to the power n minus 1 is 1. So a to the power n minus 1 by 2 is some number whose square is 1. So it can only be one of two numbers. It can be either 1 or minus 1 or p minus 1. P minus 1. In this case, actually, this is minus 1. So actually, this is a quick way to compute if something is a quadratic residue if you know n is prime.
No. In the second case, if a is not a quadratic residue, then why is it that it is minus 1?
I haven't proved it, but I want to claim that that is in fact the case. Okay. It's not hard to see this. You realize you stare at it for a while. I don't want to get into it because I have more stuff, but it's not hard to see this. Unless RP, is there a quick one-line way of saying this? Or
one thing is, so firstly, as Prahladh mentioned, I mean the non-quad, I mean a power n minus 1 by 2, because when you square it, you get 1. So it can either be 1 or minus 1. But now look at the equation x power n minus 1 by 2 equals 1. You already know there are n minus 1 by 2 solutions, which means everything else must go to minus 1. Right?
Yeah. So when n is prime, we have this. We can actually compute. If I tell you n is prime, I can actually compute the Legendre symbol, which is basically telling you it's a quadratic residue or not, because this guy is easy to compute. This is just repeated squaring. You take a, square it, you can compute a to the any power. This is an efficient compute. By the way, for this also you need to know repeated squaring, and this is something which we can do. We can do this efficiently. Therefore, you just compute this, find out if it is 1 or minus 1, and that will tell you whether a is a quadratic residue or not a quadratic residue.
This you can do in polylog n.
You can do this in time polylog n. Yes. Now we're going to do something weird. We're going to extend this definition. So extend the Legendre symbol definition to non-prime n. And this is what's called the Jacobi symbol. So suppose n is p1 to the k1, p2 to the k2, pn to the kn is the prime factorization of n. And let's assume n is n is odd. I'm only going to extend it to non-prime odd n. Okay. Then a by n, I'm just going to define it to be the product of a by pi to the power k. So this n is this, not this. Okay. The Jacobi symbol, I'm just going to extend the Legendre symbol to non-odd, to odd integers, not necessarily prime, by just by factorizing n and just multiplying whether it's quadratic residues or whether the corresponding Legendre symbols. Now the fact and now I'm going to state a bunch. So this is what is called the Jacobi symbol. So it's an So the Jacobi symbol on the face of it seems to be something. So notice the Legendre symbol. If I had known n is prime, the Legendre symbol is easy to compute. That's what we saw before. This fact told us that the Legendre symbol is easy to compute. The Jacobi symbol, on the other hand, the way I had defined it, it's not easy to compute because it requires the factorization of n. But now I will state a few facts regarding the Jacobi symbol. Most of them will follow from the definition. There'll be one which is couple of them which are non-trivial. But once you see all these facts together, we will see that actually the Jacobi symbol, even though this way of defining it requires you to know the factorization, you can actually compute the Jacobi symbol very efficiently. So let's list a bunch of properties of the Jacobi symbol. One, if A is congruent to B mod n, then I want to claim A by n is equal to B by n. This should be clear because it's two AB by n is A by n, B by n. This is true because the Legendre symbol satisfies this. The Legendre symbol itself satisfies it. If you multiply two quadratic residues, you will get a quadratic residue. If you multiply a quadratic residue and a non-quadratic residue, and that's all. You can all see that all from this one. If you multiply two quadratic residues, it will remain a quadratic residue. If you multiply a quadratic residue and a non-quadratic residue, it will be a non-quadratic residue. If you multiply two non-quadratic residues, it will become a quadratic residue. And all that's got from this fact. So the Legendre symbol satisfies this property. Therefore, this Jacobi symbol will just inherit it from the Legendre symbol. Then 3. The same thing happens in the denominator, AMN. And this is true almost by definition of the.
The third equation, the right-hand side is A by M times A by N.
Yeah. This is true by definition, the way I define Jacobi symbol. Then the most interesting of them is the quadratic reciprocity. It says that if m and n are odd positive integers, then these two Legendre symbols are exactly just -1 to the power m minus 1 by 2 to -1 to the power n minus 1 by 2. So if I know this if I know this Jacobi symbol, I know the other Jacobi symbol. It just differs. Notice Jacobi symbols can only be 1, -1, or 0, because it's just a product of the Legendre symbols, which are 0, 1, -1. And this says if I know one of these guys, I know the other guy. This follows from the corresponding fact for the Legendre symbol. This is Gauss's quadratic reciprocity law. I will assume this. This is a non-trivial fact. We will assume this. And we will see the power of this very shortly. I'll need one more thing and then do it. Then I want to say, if suppose you had left with 2 over n, this I want to claim is just minus 1 to the power n square minus 1 by 8. And once again, n is an odd. People are with me so far? So now I want to say, I'll just give you an example of a thing I'm actually going to take the example which is on Wikipedia. I'll show you the example, this one, and show how to compute the Jacobi symbol using these properties. And so if you have ever seen, I'll first do run an example, and then you'll see that it's very similar to another problem that you have seen, another efficient problem that you're most likely seen. This one. So suppose I want to compute the Legendre symbol of 1001 over 9907. Of course, one way of doing this is factorize the top, factorize the bottom, and then use the Legendre symbol, use the actual definition I gave. But that requires you to know factorization. And that's a hard thing. And I don't want to do factorization. So what I'm going to do is I take this number. You know that by property 4, this is the same as 9907 by 1001 times minus 1 to the power 9907 minus 1 by 2 minus 1 to the power 1001 by 2, which happens to be 1. Therefore, this is just 9907 by 1001. But now I will use property 1. If A is congruent to B mod n, then A by n is equal to B by n. So I can just reduce 9907 and you will reduce it to what? This will become something like, I'm just reducing it 898 1001. Now, an even number has entered into the picture. So let's just factorize it. I'm going to take 2101 by 449 1001. This is definition. This is once again follows from the Legendre symbol definition. This 21001, we know we can calculate it using property 5. It happens to be 1. So this is just this is just 449 by 1001. Now once again you flip. This is 1001 by 449 into certain minus ones. You'll realize that minus ones are 1. Therefore, this is just this. But once again, now you can further reduce it. This is 103 by 449. Then this becomes 444. Then once again, you can use quadratic reciprocity to flip it and find what's the minus 1. It happens to be 1 again. Great. Once again, now you use remainders. You get 37, 103. Then you flip this again, 103 by 37. 29 by 37.
Looks a lot like Euclid's GCD algorithm.
Exactly. This is exactly like Euclid's GCD algorithm. In fact, the answer finally turns out to be minus 1. So I'm just using the properties I stated above, and I show you that this actually gives you an efficient algorithm for the Jacobi symbol. The Jacobi symbol is something which we can compute efficiently because of the quadratic. The main thing over here is the quadratic reciprocity. It lets you do this flip. It lets you go from m by n to n by m. So you can always put the smaller number on the top, and it lets you keep doing this repeatedly. Sorry, it lets you put the bigger number on the top, and then you can take reminder, make it smaller. So you can, and this is exactly how Euclid's GCD algorithm works. So in fact, you can show that the running time for Jacobi computation is exactly the running time for, you can show the same analysis will give you the running time for the Jacobi algorithm is also the same as the running time for the Euclid's algorithm. The same bound you get is also bound for the computation of Jacobi algorithm. So Jacobi algorithm actually runs in polynomial time in its input. In fact, it's so the conclusion of this is
the minor point in the quadratic reciprocity definition, maybe you will want to put m over n and n over m on two sides of the equation. Because I think otherwise when one of them is 0, then you get into trouble. So you just write it as m over n equals -1 per this, -1 per this times n over n.
Oh, you want it like that.
Yeah.
Okay.
So that, if they are 0, they're both 0.
Okay. They are 0, they are both 0. Conclusion is Jacobi symbol A by n can be computed efficient. In fact, in time, if you do the analysis, this will just turn out to be log n into log a. Okay. Now, given this, the Jacobi symbol has an efficient efficient way of being computed. But we know if n is prime, this guy a power n is actually equal to a power n minus 1 by 2 mod n. What we will show is if n is an odd composite, then there exists a such that a by n is not equal to a power n minus 1 by 2 mod n. There is at least one a which does not have this behavior. I'll show this depending on how much time we have. I'll show this towards the end of the lecture, but let's just keep this. If n is odd composite, but now you can define you can define Sn, which is a subset of Zn star, as the following way. Sn is the set of all a. Let me just define it. Sn is a set of all a in Zn star such that a by n is equal to a power n minus 1 by 2 mod n. Now, I want to ask a question. Is Sn a subgroup of Zn star? Multiplicative subgroup.
I guess yes, because properties above.
Properties
above, I guess it is yes.
So a by n has a nice multiplicative feature about it. A power n minus 1 by 2 has the same multiplicative feature. So if a by n equals a power n minus 1 by 2, b by n equals b power n minus 1 by 2, then a into b by n is equal to a. You have this property. Therefore, it is actually a subgroup. But now you can say something. Suppose there exists, this tells you this is in the odd composite, it's a subgroup, but it's not, it is small, it is not the full group. Sn is strictly smaller than Zn star. If it is strictly smaller, if it's a subgroup, how much can it, what can be the size of Sn? So
almost half.
So if it's n, so in other words, n odd composite
inside n star.
The size of Sn has to be less than or equal to Zn star by 2. This gives you a natural randomized algorithm for it. So this motivates the following. I don't know if you can see the algorithm already. Just this fact. This one fact. You should be, the randomized algorithm should stare at your face, but let's see this. So on input n, let's pick a random A in Zn. Ideally, I would want to work with A, and this is completely at random, to compute GCD of A and N. If compute this, if AN is not equal to 1, output composite. 4. So now you know you have picked up A in Zn star. If A by N is not equal to A power N minus 1 by 2 mod N, output composite, else output prime.
Could you just go to the top where you defined SN?
So let's look at what this algorithm, let's just stare at this algorithm for a while. What does this algorithm do? If A is prime, if N is prime, what does this algorithm do?
It might output something with an error, right?
Does it? If N is prime, does it output ever output?
No, sir. We'll pick an A and GCD of A command will be 1.
You can say actually pick it in Z.
I want to make A not equal to N or something on the first step.
Yeah.
Oh.
Yeah. It's always going, it can never output composite in this case. In this case, for every choice of A, for every A, SS outputs prime. And the way I'll say this is the probability that the SS algorithm on input N outputs prime. Prime. So the SS algorithm takes, notice it takes two, it has the real input and it has a random input. It picks an A also. Let me drop the A for now. It's a randomized algorithm. It has 1 over the choice of A is 1. But what if N is composite? So it is going to output 1. It is going to say composite most of the time, except when it picks an A which happens to satisfy this inequality. In other words, it outputs SS else if A belongs to Sn. So you can write probability A SS N equals prime. N equals prime. This is the error. This one is certainly Sn, size of Sn by Zn star, which is less than or equal to half. So it errs with only probability half. So this is an algorithm. It's a very simple randomized algorithm. All the steps in it are very, so one thing which we haven't seen is quadratic reciprocity law, but when that the algorithm is extremely trivial to implement. We have more or less seen the entire, this one. All the computations over here are very easy. The GCD algorithm, you know how to do. This is repeated squaring. Jacobi symbol, we more or less saw how to do it given quadratic law of reciprocity. And there's one more fact which I didn't mention, this fact. It was this fact which, if it's odd composite, there always exists some A such that it doesn't satisfy this inequality. We'll see this shortly. I'll see this, but we'll defer that to the end of the lecture. But I want to say, given this, we have this nice one. We have an algorithm which, irrespective of the input, if the input were prime, it's always going to give the right answer. If the input were composite, half the time, it's not half the time based on the input, half the time based on its internal random coins, it is going to give the right answer. Only half the time it fails. So now you could just repeat this algorithm some 10 times and make the error to be like 1/2 to the 10. So it's an extremely efficient randomized algorithm that checks if a number is prime or not. And all of this just comes from this simple fact that the things that violate your condition being checked, the things that violate this condition form a subgroup, and because it's a subgroup, it can only be half the size of the, it has to be smaller by at least a constant factor, and hence with at least probability half, you will recognize that it is a composite number if it were composite. There's a probability of you erring is only when A falls in Sn, and this is a very low probability event. It's probability half, and you can repeat it several times to reduce this. This is good. Okay, so far. So this is not a type of algorithm which you have seen so far. This is a randomized algorithm because the algorithm is tossing random coins. It's picking, this step of the algorithm is something which we haven't seen so far. It is picking a randomized this one, but because of this one step, it makes the algorithm extremely effective. It's a very simple algorithm to solve primality. Any questions? So this is one of the earliest algorithms which showed that primes can be solved efficiently if you allow the algorithm to toss random coins. Okay. So I still have to prove this one fact, the fact in gray. We'll defer that to the last 10 minutes of the course. I'll do some more examples and then get to that. If I don't have time, I'll post this as a note on Academy so you can see it. It's just a bit of number theory. You will just have to show that for every composite number, I can produce an A, and we'll just show how to explicitly produce an A that has this property. Okay. Any questions on this? Okay. So we'll move on to our next example. We'll move on to our next example. Our next example will involve what's called the polynomial identity testing. And here, the basic question over here, let me start with the basic question and then we'll see some applications. I'm going to give you a polynomial P, a multivariate polynomial P, in, say, some field. It's x1, x2, xm. These are the m variables. Actually, let me call the variables n. Variables in some form. There are several ways of presenting the multivariate polynomial. One, I could give you the polynomial representation. I could give you monomial by monomial what it is. But in some form, I'll tell, it will come to, the question is ill-formed because of this part of this one, in some form. And the question is P identically 0? So is the polynomial P that I present you actually the polynomial which is 0 on every input? Is it identically 0 polynomial? Of course, this is, notice, of course, it's easy if P is given in the monomial representation. You just need to check that every single monomial is 0. If a monomial is non-zero, it's a non-zero polynomial. But we are not going to say, well, what do I mean in some form? There are several ways. I'm not going to formally define this, but there are several ways in which you can give it. So I could possibly specify the polynomial as the determinant of, say, I could give you the polynomial as x1 plus x2, x3 plus x5, 0, x8 plus 6x9. So I give you this and I say the determinant, the P is actually the determinant of this polynomial. And I'm asking you, is the determinant of this polynomial is some multivariate polynomial, and I'm asking you, is this determinant trivially 0 or not? It could so happen this determinant is 0. Okay. For example, if I had given you this polynomial instead, if I had given you x, y, z, x prime, x1, y1, z1, x2, y2, z2, x1 plus x2, y1 plus y2, z1 plus z2. If that was this one, the determinant of this is 0. It's formally 0. So, but on looking at this, you can't say it's not obvious that the determinant is 0. Of course, this one is a special form. You can see it's 0. So I'm going to give you this. Particular, what you can ask is the polynomial. One way of presenting is presented as an arithmetic circuit. What do I mean by that? So they are an arithmetic circuit is similar to a Boolean circuit. It's a DAG. It's a DAG. Its inputs are the variables x1 to xn, and possibly its inputs are the variables, or say field constants, 0, 1 field constants. And the gates are either multiplication gates or addition gates. For example, I could give x plus y into z plus x. I feed both this, and that's the final output. That's one arithmetic circuit. And I'm asking you, is the polynomial computed by this arithmetic circuit the identically 0 polynomial or not? Okay. Why is this called polynomial identity testing? So typically, the usual thing is you're given two polynomials and you ask two different polynomials and you ask, are these the same polynomial or not? In particular, asking is the difference of these two polynomials the identically 0 polynomial or not. This is a commonly, we will see this. In fact, a large part of the rest of the course will be based on this particular problem, trying to find out ways and means of doing polynomial identity testing. It is given two polynomials, find out if they are exactly the same polynomial or not. And what we'll show is, we still don't have an efficient deterministic algorithm to solve this problem in its generality. But what we'll show is that, once again, the effective power of randomness, we will show a very simple randomized algorithm that will tell you if a given polynomial is 0 or not. Okay. And this, the heart of this is based on there are several names for this lemma. One of them is what's called the Schwarzschild lemma. So for the Schwarzschild lemma, the polynomial identity lemma, this has been, it's a very basic fact. It has been proven several times over in the last 50, 60 years. We'll see this, and this will be the heart of, it says the following thing: let P x1, x2, xn be a non-zero. So it is a non-zero polynomial of total degree. What do I mean by total degree? The degree of a monomial is the sum of the degrees of its individual variables. And the total degree is the monomial with the largest degree of the set. So total degree at most D. And S is any subset of F, any finite subset then the probability, so I'm thinking of this as, so think of this picture. So S bar M is
Prahladh, do you have an iPad charger?
plug it in 1 second. And P is, this is the place where P is 0. What we're going to ask is, if I pick a random A in S to the M, S to the N, what is the probability that P of A is 0? I want to claim this is at most D over size of S. Is the statement clear? Notice this, if P were univariate, this is something which we have seen already. This is what we talked about at the beginning. If a P is a univariate polynomial, it can have at most D roots. So in particular, in a set of size S, the number of roots can be at most D over S. Possibly it's even smaller than that, but the number of roots is at most this. This is just an extension of this simple univariate fact to multivariates. The statement clear? We'll just prove it. We'll just prove it by, it's a simple proof by induction, and let's just see this. So it's, so, but before that, let me state what is it. So it says if there is, let's state what it, let's try to find out what it means. It says that if you have a non-zero polynomial, it cannot be 0 at too many places. If S is large enough, compared to D, then once you know the polynomial is non-zero, it has to be non-zero at almost everywhere. At 1 minus D by S fraction of the place, it has to be non-zero. It can be 0 only at a very small, this one. And so this naturally tells us that if we'll frame several of our problems in this fashion, we'll get down that the problem is an S instance if the corresponding polynomial is identically 0. And then to check it's identically 0, just pick a large enough S and choose a random point and compute that polynomial, whether it is 0 or not. This is going to be this one. But let's see the proof of this. So you want to, so let's write. The proof will be by induction. So base case n equals 1. Of course, we know that it is true in this case. Let's assume it's true. True for up to n minus 1. So now I'm going to write the polynomial p x1 to xn. Let's write it down as x1 to the power. So let's write it x1 to the power t, p to the power t, x2, xn, t itself going from 0 to some what can it go to? Some e, where e is some number less than or equal to t. So let the largest degree of the polynomial in the first variable be e. Then you write it as a univariate polynomial in x1 club, combining all the other things. You view this as a univariate polynomial in x1 and whose coefficients are themselves multivariate polynomials in the remaining variables. I'm just writing it down this way. Now the process of picking a in S to the n. So what is this A? A is actually you're picking A1, A2, AN in S cross S cross S. This process, we can think of it in two ways. First, we pick A2 to AN, and then you pick A1, the random process. So you can ask two things. First, let's look at this. So what do we want? We want the probability that P of A1, A2, AN is 0. So It might so happen. So I'm going to do this by picking of this A1, A2, AN in 2 steps. First, I'll pick A2 to AN. It might so happen once you pick A2 to AN into this polynomial already vanishes. It becomes a 0 polynomial. That is, all the PTs vanish. All the PTs as t goes from 0 to e vanish. In which case you can't do anything. No matter which A1 you pick, this is going to be 0. In particular, it says PT should also vanish. This particular polynomial should also vanish. Notice the degree. So we are going to split this into 2 cases. This is the case that this is less than or equal to probability that P E of A2 to AN being 0. In this case, I'm going to completely give up and say the PE is the coefficient of x1 to the power e. Okay. Plus the probability that PE of, I'm going to be in for trouble today, is not equal to 0. Let's write this. I want to say, let's look at this polynomial. Summation t equals 0 to e, a1 to the power t, pt a2 to an is 0, conditioned on pe of a2 to an is 0. Okay. Either the leading coefficient, this leading coefficient is
conditioned on p not equal to 0.
Sorry, not equal to 0. Either this leading coefficient, when you plug in A2 to AN becomes 0, or if it's not 0, then when you plug in AN, does it become 0 or not is the question I'm going to ask. Okay. So how can I bound this? The first one is by induction. It's a small lower order thing. This is, what is the degree of this? The degree of this is exactly d minus e by size of s. That's the degree of p. And this guy, this is now a degree e polynomial. It's a univariate setting now. It has this, so this is exactly d by size s. End of. Okay. So this is the Schwarzschild lemma. It shows that if you pick an s which is considerably larger than the total degree of the polynomial, any non-zero polynomial, if it is non-zero, can be 0 only at a very few locations. It can't be 0 at too many locations. Okay. Even this. So now let's see actually a stunning example, an application to matching of this problem. So I'm given, so the input, so given a bipartite graph, GLRE with size of L being size of R, does G have perfect matching? Let's look at this problem. We have designed in an algorithms course, so this is bipartite matching, by matching. In the algorithms course, you would have designed efficient algorithms, deterministic algorithms to come up with something as a matching or not. We will see the power of randomness. In fact, the power of the Schwarzschild lemma to come up with an extremely simple randomized algorithm that solves this problem. Okay. It might not be obvious right now, but I'll construct one particular polynomial P. And once you stare at the polynomial, it should be clear that there is a randomized response. So let's construct. So I'm going to look at this is not the adjacency matrix. You're going to put L and R. You're going to put it's the bipartite adjacency matrix. So it's a bipartite adjacency matrix. You put 1 if this particular vertex U is connected to this particular vertex V. in the bipartite graph. It's not the usual adjacency matrix. The left-hand side is only L, the right-hand side is only R. But this is a square matrix because L is equal to R. That's only when you have, so we are assuming L is equal to size of L equals size of R. Therefore, that's the only cases when you can have a perfect matching. So we're working in the case of square, it's a bipartite matching in which the corresponding bipartite adjacency matrix is a square matrix. Okay, there's a square matrix. So the bipartite adjacency matrix, basically this M is exactly what is it? So M of U comma V is 0 if UV is an edge. Sorry, if UV is not an edge, and 1 otherwise. Okay, so let's look at this matrix. But this is a matrix of just scalars. Now I'm going to come up. Let's bring in variables. Consider the following formal variables. Consider the variables x uv for every uv in the edge set. So let's look at the polynomial mx bar, which is defined as follows. Mx bar of uv, its uvth entry is 0 if uv is not an edge. If uv is an edge, I'm just going to put the variable xuv out there. So it's almost the same as the matrix that I drew here, except the ones get replaced by a formal variable xuv, a different formal variable xuv at every location. Okay, is the matrix clear? Definition of the matrix. Now let's stare at this. If there's what can you say about this? What can you say about the determinant of this matrix? And the fact that there is a perfect matching or not.
If it is non-zero, then there is a matching.
So every term in the determinant, or the permanent for that matter, every term in the determinant or permanent corresponds to a matching in this one, and no two matchings are going to cancel out each other in this formal this one. Notice that. So if there is a perfect matching, there will be one of the monomials of the determinant of the permanent which is non-zero, which exists. Otherwise, it does not exist. So it's a trivial observation, the fact that mx is 0 if and only if G does not have a perfect match.
Determinant of mx.
Sorry, determinant. Okay. Now, given this, how would you now solve? How do you find matching? How do you solve the matching problem?
Use PIT as a problem. Reduce it.
Huh?
Reduce the matching problem to the PIT problem.
PIT. So how would you now solve the problem?
Just start with take a subset, sort of
Find
polynomial at a few points.
Yeah, so you need to find a subset which is considerably larger than the total degree of the polynomial. What is the total degree of the polynomial?
Number of L and R, like the size of L and R.
It's in fact, it's exactly the size of L. This one, it's N, which is whatever it's the size of L. So let mod L equals mod R equals N. Choose yes, say a subset of the rationals or whatever, or the integers of size, say 10n. And just compute the determinant on, pick a random point in s to the power n and compute the determinant on this. And if it is, you know that if it is non-zero, it has to be non-zero only with, can be non-zero on it has to be non-zero on 9/10 fraction of the places, and it can be 0 only on 1/10. So the algorithm is this is an algorithm due to Lovash, by the way. So Lovash's algorithm is the following. So on input G equals LRE. So write down this matrix MX. Construct a set. Let S be equal to, just let's take 1, 2, 3 all the way up to 10n, where n is the size of R. We pick a random A in S to the size of the edges and compute determinant of M of A and output matching if output is the Z, if Z is not 0 and no matching otherwise.
This algorithm doesn't give the matching though, right? Like
it doesn't give you the matching. There's a way in which you can modify this, but that requires more work. Right now, it doesn't give you the matching. It tells you whether it's a matching or not. And how do you, by the way, if there is a matching, so which side? So what, once again, let's look at it again. If there is no matching in the graph, will it ever say there is a matching?
no.
Because if there's a no matching in the graph, the polynomial determinant of M of X is always the 0 polynomial. So it always outputs 0. So in the case of no matching, the probability that Lavache's G says matching is 0. If there is a matching, the probability that Lavache G says there is a matching will be how much?
At least something like
At least 9/10, the way I have set up the parameters. The number of points is 10n. By the way, once again, if you recall the algorithm for perfect matching, that's an extremely complicated algorithm that uses augmented paths and all of these, the deterministic algorithm for matching. This is an extremely simple algorithm. It's extremely simple. It's simple. You can actually say it's simple in several senses of the word. One, for instance, it doesn't have this augmented paths, and which is a very complicated and extremely sequential algorithm. If you stare at the matching algorithm that was done in the algorithms course, the matching algorithm is very, very sequential. You have to do this augmented paths, and it's a, if you actually go back to the notation of the previous lecture in which Ram Prasad introduced NC, AC, and this one, it's an algorithm which is sequential and does not have a shallow depth circuit that computes this algorithm at all. The usual algorithm for matching. Whereas this algorithm for matching, if it only depends on its complexity is just the complexity of computing determinant. The complexity of this algorithm is basically just the complexity of computing determinant. And determinant, there are several ways to compute it. The usual way you would have seen is Gaussian elimination to compute determinant. But determinant has a much more faster, shallow circuit implementation. In fact, determinant is in. So this is something which requires a little bit of work. You can show that determinant is in NC2. There is a very shallow algorithm that computes determinant. Therefore, this tells you that matching, I haven't defined these classes, is in randomized NC2, is in randomized NC. Bipartite matching is in randomized NC. So it says this is a considerably simpler algorithm than what we have seen, than the deterministic algorithm which we've seen in class, in the algorithms course. That's very.
It was like just Boolean circuits replaced with multiplication and addition gates, right?
Which one?
Here, determinant belongs to NC2 is like just the Boolean circuit version replaced with the arithmetic circuits, right?
Determinant. No. I'm meaning even in the Boolean circuit world, it is actually, you can do it's true in both the arithmetic circuit, but even in the Boolean circuit, if I give you the bit complexity of the determinant in which I give you the bits of each number in a bit representation, you can compute the bits, the output, the bits of the thing in a circuit which is just which is
how do you define determinant in the Boolean world?
It's determinant is just a bunch of your, it's a function which takes n square inputs, each input of say log m of m bits each, and it has to output some other number of so many bits long, which is the final answer. So you're thinking of it from bits to bits. So it's n square into m bits to, you know, some other, another poly m bits. Question is, how do you go from this to this? And there is a circuit. So I'm even in the Boolean complexity, it's actually, you can define it even in the Boolean complexity world is all I say. Okay.
I guess there is a randomized algorithm by something related to weights by MVV.
Which one?
Vazirani gives a weight randomized quasi.
No, that's the modification of, that's a strengthening of this algorithm which you see just now, which not only tells if there's a matching or not, it will actually output the matching. It will give you the matching. It will takes this. This is Lowash's initial algorithm. Was the Vazirani-Mulmele algorithm is actually, it takes this as the basic thing and then goes on to actually find out the matching. And it says you can find out the matching also very efficiently, much more efficiently than what we did in the deterministic world. Okay. I'm really short of time. I wanted to do one more problem. But let's, what do I do right now? Actually, let me start the other problem. I will push there was something I promised to do, which is showing if A is composite, then there is an A such that the Jacobi symbol for A is not equal to A to the power n minus 1 by 2. This is just it's just, I just have to show you such an A always exists. I'll just post this on Academy at the end of the lecture. I'll just post those notes. But now let's go on to our next one. I want to talk about another interesting problem, which talks about quadratic polynomial factorization. I shouldn't take more than 6 minutes for this. Let's see. Or equivalently, this can also be said as finding square roots. Okay. So suppose I give you the polynomial x square plus, so let's actually work with something even simpler. Should I do this or should actually we will do this next lecture. It might take me, I think I will do it in 5-6 minutes, but I will take longer than it. Let's stop with this. So I will do quadratic polynomial factorization and define the probabilistic classes next lecture. But then if you have any questions for the two problems that we talked about. Both the problems were both those two problems and the quadratic polynomial factorization, just to illustrate the amazing power of randomness. Randomness helps you to give extremely clean and simple algorithms in several instances. Any questions? So we'll do this next time.
I just wanted to ask something not related to this lecture. So there's these there's supposed to be these machineless characterizations of complexity class, right? Like Cobham's class, like thing for P and so on. And there's this interesting note in Aurora Barak, which is that so we studied about diagonalization and like that any proof for P versus not in P should have this non-relativization thing. So they're like, if you include this principle of local checkability in your axioms of defining a complex like P, then you will always get the results that you expect. I've kind of like never seen these kinds of topics in like the two complexity theory courses that I've seen.
Actually, even I haven't seen these things. If you can point me to this, I can have a look at it. Does Aurora Barak itself mention?
Yeah, he just mentions it. He mentions Immermann's work on characterizing many of these complexity classes via logic formulas.
Yeah, so there's one on descriptive complexity that's there, and then there's this unpublished manuscript by Arora, Impagliozzo, and Vazirani, which is basically saying that if you include this principle of local, like that computation is local formally, then you can, then you can show that basically all the results that you expect in complexity, you get them. Like separations and so on. So yeah, I'll post this on Acadly. Yeah,
okay. I haven't. I know. Okay, you know that Professor Immerman has worked a lot of this. The Immerman, possibly even Spellman, has worked a lot on this sort of this one. But somehow this is not taught in standard complexity classes.
Yeah.
Okay. Okay. Let's break now. Meet on Monday. By the way, the next problem set is.
Oh yeah, I'll post it soon. And I'm also hoping at least by the weekend or something, I'll finish correcting problem set 1.
Yeah.
Yeah, you'll get your things then.